We are actually shifting towards a new kind of the new method of solving problem, where we take some differential equation of second order and particularly recognize them as heat equation that is parabolic equations, I mean, and or harmonic equations or Laplace equations or elliptic equations, or towards some wave equation, which are actually some the hyperbolic equations, and how will we solve them whenever some boundary conditions will be properly given. Now I'm directly trying to go towards the problem and just follow step by step and see how we solve. So this will be our class number 19, and the first problem is saying that you have to solve a heat flow equation, and this is given as, this is conductivity del to u del, actually you have to solve u of xt, where your given differential equation is this, and you have to use the method of separation of variables. Now question is, in such a case, how we will solve these things. Now as it is told that we have to use the method of separation of variables, we will suppose that, say if we have to find out this uxt, and we tell that this uxt is separated in two different functions. One is with argument x and the other is completely with argument t. So just follow now. If we impose this in this given equation, what we get? See, so this is k or kappa, whatever you write the conductivity as. This will be, see, this part is only depending on t, so the differentiation, partial differentiation with respect to x will not affect this part, so this will go out, and this part will be differentiated twice with respect to x. And see, this is only a function of only x, right? So whenever you are writing partial derivative, actually that is equal to the total derivative, because this is a function of x and you are taking partial derivative with respect to x only. So I am writing this is d2 x dx2, okay, and this is equal to, from there you can see this x part will coming out of the differentiation, and by the same logic this will be dt dt, okay. So if we take all the x in the same side, what we will get? See, so we have 1 over x of x from this side, d2x dx2 is equal to 1 over kappa t dt dt, right? So follow one thing. If kappa is the constant, is one constant, then this part is completely a function of x, right? And this part is completely a function of t. Now how can that be possible? Because this is a function of x and this is a function of t. They cannot be equal to each other, right? Only except the case both of the functions are equal to some constant. So we take this is equal to some constant mu, say. So you get two differential equations. Number one is d2x dx2 minus mu x of x is equal to 0, and the second one is dt dt minus mu kappa t of t is equal to 0. These two are two equations you obtained. Now we will solve the first one. Now see, the point is your mu can be 0, your mu can be positive, or your mu can be a negative as well. So we are in the door of solving some eigenvalue problem. So we start. Say case 1, what we get? See, first take mu is equal to 0, the simplest case. Then this is giving you capital X of X is equal to some C9, some constant multiplied with X plus some constant C10. See, mu is equal to 0, so actually the double derivative is equal to 0. So the resulting equation should be look like that. Actually, this is a straight line like y is equal to mx plus c type of thing. Now, see, from the same idea, you can say that this is equal to capital T of t is equal to some say some C11. Okay, so this is the solution if mu is equal to 0. Now case 2 is saying if mu is equal to, or say mu greater than 0. So if mu is positive, so let us assume this is positive, right? So this can be equal to some number square. Need not to be that is an integer, but whatever that be, we write it as lambda square. So, and lambda obviously will not be equal to 0, mind it. So what we get, we see your x d2x dx2 minus lambda square capital X is equal to 0, and dt dt minus lambda square k t is equal to 0. Now solving, you see, what we do actually, we take some e to the power mx as auxiliary function, and then you will having m square minus lambda square is equal to 0. So you solve m is equal to plus minus lambda, and so your equation, the solution should be some constant, say C6 e to the power lambda x plus C7 e to the power minus lambda x from this part, and from this part that should be capital T is equal to some C8 e to the power lambda square kt, right? Okay, now third case, case 3. Now in case 3, obviously mu is less than 0, so we assume that this is equal to some minus of n square, because this is equal to 0 and this n is not equal to 0 obviously. And to solve that, what we will get, see, the equations are d2x dx2 plus lambda square x is equal, sorry, this is n square x is equal to 0, and here dt dt plus n square kt is equal to 0. Now from this part you will be having a solution, as again you will take some e to the power mx as the auxiliary function, and m will be equal to plus minus ni, and whenever such a complex number comes or an imaginary number comes, we know that the solution looks like some cos sine thing, and this is actually equal to capital X of x is equal to C3 e to the power, sorry, this will be cos of nx plus C4 sine of nx, and from there we have capital T is equal to some C5 e to the power minus n square kt, isn't it? So there are various possibilities of solution, right? Number one possibility, for check that, from there you can write u of xt is equal to C11 multiplied with that, say this is C12x plus C13. So this may be a possibility. Okay, next one, from there you can write this C8 and C6 will be multiplied, so this will look like e to the power lambda square kt multiplied with C6 multiplied by C8, say that is equal to some C14. C14 e to the power lambda x plus C15 e to the power minus lambda x. So that may be a solution, and for the last case your solution may be uxt. This is equal to, again, C5 will be multiplied by C3. We write it as C1, and see, this one is at the outside multiplied, minus n square k t in a bracket C1 cos nx plus C2 sin nx. Okay, so this may be a solution, but we'll follow one thing, that is, whenever you are writing such a thing, this solution is depending on the value of n. So actually this can be written that this is some unx, right? Because this is mandatorily depending on the n. And see, we know that whenever you have a linear differential equation, if you get some solution, say small f1 xt, small f2 xt, etc., they are solutions of the differential equation, same differential equation, then obviously their linear combination will be another solution, because due to the linearity. So the summation of this function unxt for all n, every possible n, will be another solution. Okay, so we will be going towards the next problem. In the last problem, follow that we have not mentioned any particular initial or boundary condition, but for this problem we will be imposing some conditions. Slowly we will be imposing the conditions and we will check what is happening. So the problem given is, you are given an equation del 2z del x2 is equal to 1 over kappa del z del t, and what you have to do, explain the method of separation of variables for finding solutions and of second order partial differential equation given by this, and hence find the solution of one-dimensional diffusion equation. This is the one-dimensional diffusion equation because you see their only spatial dimension, spatil, spatial dimension is x, and this is time. So you are in one dimension actually, and in one dimension you will follow that with time how your heat or how your temperature gradually increases or decreases. This is actually the physics of this problem, and this solution should be confined by one condition, that is, whenever t is going to infinity, uxt should be going to 0. So actually this is meaning that when infinite time will be passed, then your temperature will be almost 0. Everything will be cooled down. Okay, so let's start again from this equation. See, I mean, just now we have done everything. We know what should be the general format of the solution, but still let us calculate, okay, to get habituated with that. So I am taking that your zxt, don't get bored please, because I am calculating in the same way we have done before, and we are trying to find the solution. So or actually if you don't, if we don't need to do all these things, then actually we have a solution here, right? Let's check what is going what. So see, one possibility was, the first possibility was that, okay, so for case 1, if you take mu is equal to 0, then your solution is zxt is equal to c12x plus c13. See, there is no way that you can impose some value of t, and it is showing that this will not go to 0 for that. See, this is equal to 0 at zx infinity. So this is saying, I mean, this is true for every possible x, right? So this is only possible whenever your c12 C12 and C13 are equivalently or identically equal to 0, because see, else this cannot give 0 for every x. Because whatever be your x, this should be a true. So this is leading us to a trivial solution, right? We don't want that. Then case 2. Case 2 is saying, follow that this is the solution. So this is zxt is equal to e to the power lambda square kt c14 e to the power lambda x plus c15 e to the power minus lambda x. This may be this may be another one. Now follow that. For this problem you have to put t infinity, and t infinity should make this solution is equal to 0. Now follow that this part is blowing up whenever you are giving a infinity value to t. So to make that 0, your C14 and C15 both should be equal to 0. So again, identically this thing is equal to 0. So this is another trivial solution. So come to the third point. So case 3. So as you see, your case 3 is z in xt is equal to e to the power minus n square kt c1 cos nx plus c2 sin nx. This is the solution. Now follow that whenever you put t to minus infinity here, this part goes to 0 and this is multiplied with the whole, so the whole part is going to 0. So this may be a possible solution. Still you cannot determine what is your C and what is your C1 and C2, but still this may work as a solution. So for this problem, this one should be treated as a solution. So let's go for the next problem. So what you see, to determine C1 and C2, we will be needing some more conditions, right? So let's start. So this problem is saying, the third problem is saying, use the method of separation of variables to solve the equation del 2v del x2 del v del t. That is actually your kappa is given to be 1. Given that when t is tending to infinity, your v should be equal to 0, and v is equal to 0 when x is equal to 0 or x is equal to small l. Now again, we are not, see, whenever in exam you have to solve that, you have to actually go through all these terms, okay, and then again follow that by this condition, you know, this solution cannot, this will be trivially 0 and this will be trivially 0 as well. So you have only left with the third condition, right? So case 3, I'm not writing case 1 and case 2. Suppose this problem comes to your examination, then you have to solve all this case 1 and case 2 and show that they are trivial solutions. Now case 3, when your mu is less than 0 and we have supposed that mu is equal to minus n square, then your solution, follow that for this problem your kappa is equal to 1. So this is giving you v x t is equal to e to the power minus n square kappa. Now kappa is equal to 1, so n square t c1 cos nx plus c2 sin nx. We should write a n here as well. So now come to the point, we have two other conditions, right? Let's work with them. So x is equal to 0. So x is equal to 0. So Vn 0t, which is equal to 0 as given there. This is equal to e to the power minus n square t. Now x is equal to 0 means this part is 1. So c1, and this part is equal to 0. Very good. And Vn small l t is equal to 0 as well, and follow that. See, already this part was 0 and this is 0 means, because e to the power minus n square t cannot be equal to 0, right? Always it is not 0. So whenever you are writing such things, so C1 should be equal to 0. So this part has been dropped. So this part is only there. So C2 sine of n L. Right. Now see that this is equal to 0. Again, e to the power minus n square t. It is not equal to 0. Now whenever this is not equal to 0, so you are left with C2 multiplied with that is equal to 0. Now you can say that C2 is equal to 0, simple, right? But if you write that your C1 is already 0, C2 is 0, then you will be tending to a trivial solution. You must not do that. So what you will take, that your sine NL is equal to 0. So actually what are you doing, that you have taken your mu to be some n, minus n square, and you have said that this n is not equal to 0, and whatever be the n, you should be having such a solution, and the summation of such solutions over n, that should be another solution. So it may be happen for many values of n, your solution, this solution will vanish, but for many n, this will not vanish. We are actually finding them out. So among the elements of which you are taking the summation, among those elements, some are being vanished, and some elements, they are not equal to 0. So we are only keeping them. We are trying to finding them. So we are saying that, see, sine of NL is equal to 0 in such case. Now this means NL is equal to some say m multiplied with pi, when your m is equal to 1, 2, 3, etc. Right? So you can ask me that, sir, 0 will, m is not equal to 0. That's very good. But why m is not equal to minus 1, minus 2, minus 3? Even you take it to be minus 1, minus 2, and minus 3. Follow that. In this part, that will be a minus, and this minus will go out because this is an odd function. And so what will happen? Suppose you are saying sine some k multiplied with something plus sine of minus k multiplied with something. This minus will come out, and this 2 will make, suppose some c1 is multiplied here, some c2 was multiplied with that term. So ultimately that will be c minus c2 multiplied with sine of nl, right? So there is no meaning if you write this to be minus 1, minus 2, etc. So we are here, and small n, so this will be capital M pi by L, right? So now you can write your solution as, just give me a minute, you can write your solution to be Vn x t is equal to, see, this is directly giving you that you can input there. So e to the power minus n square, or sorry, m square pi square L square t, and c1 is vanished, c2 is only remained. So there will be a c2 sine of m pi L x. This is your solution, solution for n. And you know that there are many such solutions, right? And combining them, you can write that Vxt is equal to, for n equal to 1 to infinity, we are not taking the minus sign because that will give us just that, as I said, that some constant, say some C15 minus C16 type of things only, if we even add the minus things. So this is C2. Actually, I made a mistake, how? Let me show that. See, this is n. Whenever this u, I write a suffix n there, then there should I write some n, because there will be many solutions, right, for n equal to 1, equal to 2, or other values. So for every n, this c1 and c2 are different, so we should write some suffix there as well. So for now, only for this problem, I am just writing there should be an n, 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 there should be an n. So this will be an n. So C2n. Now your finally solution is e to the power minus m2 pi to l to t sine m pi by lx. This is the solution. So see, still we are left with one constant, right? So we need another condition. So see, whenever you are giving some condition on t, that is with some time, that's why we call them initial conditions, because initial or final, these terms are actually really related to some time things, right? At the first time you are doing something, that's why you are saying that this is initial. That is something starting up with, and starting up with that part, that phrase or that statement goes with the time only. So whenever you are giving the conditions related to time, this is some initial condition. And whenever you are giving some boundary to your solution to get propagated, like see, as you have done there, x is equal to, where I have written, x is equal to 0 or x is equal to L. So actually what you are doing, suppose you are taking, there is an wall, and you are taking a string, have taken some conductor there, and you are imposing some temperature here. See, your VXL, there is some temperature, and your VLT, there is some temperature, and V0T, there is some temperature. These are temperature, right? So how much heat flow will be from this thing to this thing, or this side to this side? That we are actually calculating. Like at this point, at VXT, at XT, what should be the value of V? What should be the temperature, right? So this we are calculating. So to be followed, the initial, these are two boundaries in the space. If we say like in one dimension, একমাত্রিক ক্ষেত্রে তুমি এটা পাচ্ছ, অথবা if you say in that in two dimension, দ্বিমাত্রিক ক্ষেত্রে তুমি সেটা পাচ্ছ. So we call them boundary conditions, because they are spatial boundaries. Spatial, S-P-A-T-I-O-L, not S-P-E-C-I-L. So whenever we are giving values at boundary, we will call it a boundary value problem, and whenever we are giving initial or final values, we will call them final value problem. Now point it, we have given only one boundary value problem, one initial value. So whenever you have left with one constant here, unknown constant here, right? So if we give you two boundary conditions and two initial conditions, and these initial conditions physically they do mean that you are saying about some suggestion size, or you are giving some initial velocities, or you are giving some initial displacement. If you are giving two such values, then you can even reduce down this initial constant as well to some known value. So we will proceed towards some other problem where we will give such problems, and we will show you that by them we can actually define a solution without any arbitrary constant. So proceeding towards the next problem, it's saying if both the ends of a bar of length A are at temperature 0. So we are saying whenever your x is equal to 0 and x is equal to A, temperature, say we take it temperature be a function of x, and this, sorry, function u, and this is with the argument uxt. Now when you are at x equal to 0, this is equal to 0, and when you are at x equal to a, this is equal to, or write xt at x equal to a is equal to 0. So the problem is going like, if both the ends of a bar of length a are at temperature 0. So point it, we have taken the one-dimensional direction, this is the origin. Okay, so follow that. I mean, we will not write all those stuffs, but just understand that we have placed our bar along the x-axis, and this is from 0 point to a point. So again, coming to the problem, if both the ends of the bar of length a are at temperature 0, and the initial temperature is to be prescribed function fx in the bar. So initial temperature, see, for every point 0 to a, there should be some initial temperature. How? I am writing this as ux0 is equal to some f of x. Suppose if you are at that distance, if that is some particular x1, your initial temperature will be some f of x1. Now point it, x should lie from 0 to a. And next, again, I'm coming to the problem. If both the ends of a bar of length a are at temperature 0, and the initial temperature is to be prescribed function fx, small f of x in the bar, then find the temperature at a subsequent time t. Now this is the initial temperature. Now at a subsequent time t, you have to find out what should be the temperature, that is, what should be the value of u of xt. Now just to write, so this is the initial condition, I'm just writing IC, and boundary conditions are 0xt is equal to 0 and small at is equal to 0. These two are boundary conditions. Now suppose I'm taking the conductivity to be kappa, so your heat conduction equation that should look like this, del u del t. Now let us start with the problem. So we are taking the method of separation of variable. We are taking u of xt is equal to some capital X of x and capital T of small t. Now point to be noted, whenever we are taking such a thing, then what happens for this thing? So you see that your x0 t that is equal to 0, and what does that mean? Now whenever for every t and of t cannot be equal to 0, because if you take that will lead you to uxt is equal to 0 identically, and that will lead you to a trivial solution, and we don't want that. So obviously your x0 is equal to 0. Similar run xa tt is equal to 0, which gives you your x at small a is equal to 0. Now so these two equations has been changed. So from the very first, let us see. So this is d2x dx2 is equal to 1 over k t. T is coming from this side, okay, and this part dt dt, and this part, that one x will be there, and this has come to this side, and again we see that this is a function of x and this is a function of t, and they cannot be equal unless we take them to be some constant mu. And follow this, we have done them all before. So d2x dx2 minus mu x is equal to 0, and dt dt is minus mu k capital T is equal to 0 as well. Right. So these are two eigenvalue equations. We take mu is equal to 0, case 1. Now mu equal to 0, this leads us to x is equal to C9 x plus C10, and T is equal to let us think for now this to be don't go for that. Again, and that we know that some e to the power mu kt etc. that will be coming. For this problem, this is enough to study. So see, x0 is equal to 0. Right, we have found that out, and this is C9 multiplied with 0 plus C10. So C10 is equal to 0, right? So you are left with C9x only. Now x at A is equal to C9, which is equal to 0, C9A, and C10 we have found already, this is equal to 0. So see, A cannot be equal to 0, right? Because this is the length of your bar, and so your C9 is 0 as well. So your x is identically is equal to 0. So whatever be your value of capital T, you find that your uxt is identically is equal to 0, which is leading you to a trivial solution. So we don't take that. Now case 2. This is mu greater than 0. Say mu some lambda square, and lambda is not equal to 0. So from the first equation, you know that we have x is equal to some C 6, take it, e to the power lambda x plus C7 e to the power minus lambda x. Now whenever you are taking x0 is equal to 0, you have C6 plus C7, right? Now this is one equation, and xa is equal to 0, then C6 e to the power lambda a plus C7 e to the power minus lambda a. Now see, these are two equations of C6 and C7, and they are linearly independent, because if you write the Wronskian of, the determinant of 1 1 e to the power lambda a e to the power minus lambda a, you see that is not equal to 0. So the solution, only one solution is C7 is C6 is equal to 0. Sorry. So again another trivial solution, because your x of x is equal to 0, that is u of xt is equal to 0 as well. So we are going to case 3. Let me write it here. So case 3, we have chosen this is less than 0, and mu is equal to minus of small n square, n is not equal to 0. Then where we are, start with, your solution should look like x of x is equal to C3 cos of nx plus C4 sine of nx. Now see, whenever you put x is equal to 0, then this part is equal to 0. So you have C3 is equal, and this part is equal to 1. So C3 is equal to 0. Okay, so using the condition x0 is equal to 0, you will be leading to this is equal to only the second term. And for the next one, so x0 is equal to 0 gives you C3 is equal to 0, and x at n, x at a is equal to 0, that leads you to 0 is equal to C4 sine n a. Now C4 cannot be 0, because that will lead you to a trivial solution. So you can write that NA is equal to some M pi, and M is equal to 1, 2, etc. So M pi means you have your N is equal to M pi over A. So your X is equal to now C4, or rather you have chosen some M, right? So your X M of X is equal to C4M multiplied with sine M pi A. Well, next one, we're going to the next solution is for the equation dt dt, and we have assumed that this was minus mu kt and mu is equal to minus n square, so this is n square kt is equal to 0. So t is now is equal to C6, t of t is equal to C6 e to the power minus n square kt. Okay, and you know the value of n as well, so we write it here as C6 e to the power minus m square pi square by a square multiplied with t. So your solution becomes ux t is equal to, and one another thing, whenever you are writing a m, you should write a suffix m there, because you can have such many solutions. So now multiplying this two, I have C4 and C6. Same, by multiplying we can write it as C2m, this multiplying this two, e to the power minus m square pi square a square t multiplied with sine m pi by a x. Sorry for the mistake. So this is the solution. Now another step to be taken. Apology for the fact that C, you have to write a m as a suffix of u as well, right? So let's come. C. So what you have? Sorry. So your uxt is a linear combination from m equal to 1 to n infinity xt, and that is equal to, say we are now writing this is as cm, just simply cm, m is equal to 1 to infinity e to the power minus m square pi square t by s square sine m pi a by x. So this is your solution. Now last one condition is yet to be imposed. See, this is saying that whenever your t is equal to 0, this should be equal to some f of x. So we are writing f x0 is equal to f of ux0 is equal to f of x, and that is equal to m equal to 1 to infinity cm e m square pi square. So this is actually 1, right? This part I'm writing 1, and from this part this is sine of m pi a by into x. So you know that whenever such thing can be written, this is actually a Fourier Sine series. So using that, you can write your constant cm is equal to 2 over a integration 0 to a fx sine of n pi x over a dx. This is the value of the Fourier constant, and so see, I mean, whenever you do this integration, this is a known value, right? Because your fx is known. So then whenever you input there, ultimately your solution is having no arbitrary constant. So that was in the last problem what I have told, that this problem should be solved completely without any arbitrary constant. So this is the solution. Well, in this concern, I just want to remind you that whenever you are expanding some function, say fx, as a sine series in the limit 0 to x to L, then your expansion should look like this is n equal to 1 to infinity bn sine n pi x over L. I mean, we are just going to the Fourier expansion, which we have used actually to make you recalling these things. These are our BS stuffs. So bn in such a case, that should look like 2 over L 0 to L fx, this one, then this one, sine n pi x over L dx for all n equal to 1, 2, 3, etc. Now whenever suppose you are taking your L to be equal to pi, that is you are taking between 0 to pi, then this will be replaced by pi, and this is pi, means this is equal to nx, right? So writing that, whenever you are taking this from 0 to pi, then this will look like n equal to 1 to infinity bn sine of simply nx, and your bn should be equal to 2 over pi 0 to pi fx sine nx dx for all n equal to 1, 2, 3, etc. Okay. Now, if you ask me, I mean, in a more general way, I'm sorry, I mean, suppose this is, I mean, we have just only said about sine series. Suppose we are going to cosine series now. So, for cosine series, you check that suppose now you wish to expand your fx with respect to a cosine series, and your limit is from 0 to L, then the cosine series will look like fx is equal to a0 over 2 summation n equal to 1 to infinity an cos n pi x by L, where your a0 is equal to 2 by L 0 to L simply fx dx, and your an is equal to 2 by L 0 to L fx cos n pi x by L dx, where n is equal to 1, 2, 3, etc. Now again, for this term, if you take some particular case, that is L is equal to pi, then you see this will be changing to 2 by pi 0 to pi fx dx, and this part is 2 by pi 0 to pi fx cos nx dx, only nx, and this in this part as well, this will be only nx. Now if sometimes you are taking a double sine series means you have two functions, say of two arguments, suppose say f x y, then I mean, when that can arise, that also let me tell that. So see, suppose this was a one-dimensional problem, right? So if you take a two-dimensional problem, and this is equal to u x y t, suppose a function, and for an initial value, if x u of x y 0 is f of x y is something, then you have to calculate the double sine series. So double sine series is actually double summation, and over two different parameters, say small m and small n, and two sine will be there, and the constant that will be suffixing with two arbitrary things, m and n. So this was the Fourier expansion. Now we are probably at the last problem of this class. Now this problem is saying that a rod of length L, so we are taking a rod of length L with insulated sides. This insulated sides thing, actually this is a physical physical information of the system, which is saying that you will not lose temperature, or that is no heat flow will be there for any other causes which you are not concerning about. Now this is initially at a uniform temperature U0. So this is saying that initially, that is at, if your temperature is taken by U, and which is a function of x and t. Now U of x and t is equal to 0, that will be equal to U0. This is given. Now we should say that this is x must be less than equal to L and greater than equal to 0. Now the problem is saying its end are suddenly cooled to 0 degree Celsius. Ends are suddenly cooled to 0 degree Celsius. So I'm taking that this is equal to 0 is equal to LT for all t greater than 0. Find the temperature UXT. I'm just reading the problem once again. A rod of length L, small l, with insulated sides is initially at a uniform temperature U0. Its ends are suddenly cooled to 0 degrees Celsius and are kept at that temperature. Find the temperature UXT. Now, what we will do, for this problem, we can again take that uxt is equal to capital X of small x, capital T of small t, and do all those eigenvalue problem solves, and by that mu thing, that mu is equal to 0, greater than 0, less than 0 cases, and come to the solution. So just follow the last problem what we have done. Here our new problem is saying this fx, the last problem's fx is equal to u0. These two are same here. Small a is replaced by small l. Another thing, that is the equation the equation is also same. This is also same, but what I have made a mistake, you must have told me. There will be a kappa, there will be a kappa, right? And in the solution also there will be a kappa. Well, so follow that. So what we have, already we have solved such a thing, such a system. So from there only I can write our solution should look like uxt is equal to m equal to 1 to infinity cm e to the power minus m square pi square kappa by s square t sine m pi by a x. This a should be replaced by L, this a should be replaced by L. So this is the solution for this problem, the current problem, and where your Cm is equal to 2 by L, 0 to L, fx is u0 sine n pi. Oh, another thing, see, last problem, this is not n, this is m, right? This is, I'm extremely sorry that I have written that n. So this is m pi x by L dx. Well, so we have constructed the problem. Actually, the solution is done as well. But remember, if you are facing the same problem in examination, you have to go through all the construction of the solution. Now, we will calculate this Cm. So, see, this is 2 u0 by L, 0 to L, sine m pi x over L dx. So integrating, we have 2u0 by L multiplied with minus L by m pi cos m pi x over L with the limit 0 to L. Now from there we can see L cross L cancels L, so 2u0 m pi is there multiplied with, whenever this is L, so LL, so this is m pi means this is 1, and 0 means cos of 0, so this turns to be cos of 0 and cos of m pi. Cos of 0 is equal to 1, however, right, and this is actually minus 1 to the power n, if you follow, because cos of m pi, this is minus 1 to the power n. So cancelling this minus sign, we can write it to be m pi 1 minus minus 1 to the power m. So this is actually equal to 0 when your m is equal to some 2n, where n is equal to 1, 2, 3, etc. And this is equal to 4u0 by n pi, because there is 2u0 by m pi already. So sorry, I mean this is m pi, and where m is equal to 2n minus 1 when n is equal to 1, 2, 3, etc. So these are the values of Cm. Now we can write the whole solution as, so see, this part does not exist. I mean this part this is wrong if I say that does not exist. Actually this part is going to be 0. Then your uxt is now m equal to 1 to, rather we should write n equal to 1 to infinity. So c 2 n minus 1 multiplied with sine 2m minus 1 by x over L e to the power minus 2m minus 2n minus 1 whole square pi square kappa by L square t. So if I'm not wrong, this L square will stay there. Okay, so taking all the constants common, that is these things common, and this should look like 4u0 pi m, that n thing will be there, so this is m equal to n equal to 1 to infinity. This will be L over 2 n minus 1 sine 2 n minus 1 pi x over L e to the power minus 2 n minus 1 square pi square k by L square t. So now follow that. This, there is no arbitrary constant remaining, right? Now another problem can be constructed using the same methodology. That is, say there is a problem that a thin rod of length pi this is another problem. A thin rod of pi first immersed in boiling water so that its temperature is 100 degrees Celsius throughout. Then the rod is removed from water at t equal to 0, which is immediately put in ice so that the ends are kept at 0 degree Celsius. Find W of xt if heat equation a square del 2 omega del x2 is equal to del omega del t is followed. So see, for this problem your k is equal to small k or kappa, whatever you say, that is equal to small a square, and your a is equal to, the length is equal to pi, kappa is equal to a square, and your u0 is equal to 100, right? So when you write your solution following this, your solution is wxt is equal to 400, because this will be multiplied with 400 over pi, because this pi is there, and m equal to 1 to infinity 1 over 2m minus 1 sine 2m minus 1x, because now your length is equal to pi. So this pi and l, they cancels out, and e to the power minus 2m minus 1 square s square t. So this should be the required solution. I guess there will be one pi, right? If I'm not making anything wrong, there should be a pi. Just check this one. If there is a pi, then these two again will cancel out. Please check this result, whether this pi will remain and there will be an 1, or both the pi will cancel each other. Please check that. So this is the end of today's class, that is the class 19th. From class 20th we will study the same kind of problems.